Hey everyone, in this video we're going to learn about the three right-hand rules that we use to determine how the magnetic field behaves when it's acting around a wire or in a solenoid. Okay, so the first of the three right-hand rules, so I'll call it the first RHR for right-hand rule. So the first rule is used to tell us about how a wire or how a magnetic field behaves when we send a current through a wire. So imagine for a second this pencil is a wire with the tip of the pencil pointing in the direction of the current. Okay, when we apply a current through this, so as was seen in the last video, Hans Ørsted discovered that it actually generates a magnetic field in circular motions around the wire. But how exactly do we know which direction the magnetic field goes? That's what we use the right-hand rule for. So the first right-hand rule, if we take our right hand, okay, and we take our thumb and point the thumb in the direction of the current. So again, we're pretending the current goes along to the point of the pencil. So we take our thumb, point it in the direction of the current. Our fingers would then wrap around in the direction of the magnetic field. So you can see if the current is pointing in the direction of the pencil currently is, then the magnetic field would be going counterclockwise around the pencil. Okay, if the pencil is pointing down, again, we take our thumb, we point our thumb in the direction of the current, and our fingers wrap around the pencil. And this tells us the direction of the magnetic field. So drawing this on paper, we can see, so if we draw, just say, let's draw a simple line first representing our cable, our line that's that the electric current is traveling through. Let's say the electric current is going in this direction. Okay, so we would take our right hand, point our thumb in the direction of the current, our fingers curl in the direction of the magnetic field, so we see they're going this way around the wire. So they're coming from the back of the wire and up around the front. Okay, and these lines would continue. You'd find them all along and they would spread out, getting weaker the farther we move from the wire. If this wire happens to be moving, so sometimes a wire you may be examining moving directly towards you or directly away from you. In these cases, we represent these wires. If a wire is moving towards you, so coming out of the page, we represent that with a circle and a dot in the center, and a wire moving away, we represent with a circle and an X. Okay, so let's for a second take these as examples. So the circle with the dot coming out, so that is the electric current coming directly towards you, so we use our right-hand rule. First one, we take our thumb, we point our thumb in the direction of the current, which is coming directly out of the page, and we curl our fingers in the direction of the magnetic field. Okay, so we see that it's moving in this pattern, same direction as our fingers are pointing. So when it's coming towards you, our magnetic field would look like this. When the current is going away, point our thumb down, curl our fingers, and we see that it's going in the opposite direction. So again, the first right-hand rule is telling us about the magnetic field that's created when we send a current through a wire. Okay, the second right-hand rule is for when we have, when we have a current running through a solenoid. So for a sec, let's take this pencil for a second. Okay, this isn't going to be our wire anymore for the second right-hand rule. What we're going to use instead is I'm going to use this rope, which I normally is my rope I use to tie my kayaks to, but it's all I got at the moment. So imagine for a second that this rope is coiled around, okay, it's coiled around the wire, or coiled around a core. So we can use an iron core, some other type of core. So our wire is coiled around it, and we send a current through this wire. Okay, so it's going, let's say the current is coming in through here and going around, and then coming out on this side. So the second right-hand rule, what this does is it actually creates a very powerful magnetic field that travels through the center of the coil. And it's because all these coils compound, and we'll look at that in 1 second. But how we tell the direction of this magnetic field is, again, we take our right hand, so this is our second right hand rule. We take our hand and imagine your fingers are the current. Okay, so where the current is coming in, this is on the outside of the pencil. So if we wanted to follow the path of this current, we would go up the pencil and curl our hands around the back. Okay, just in the same way that the rope is moving around it. So it's going up the front and curling around the back. Our thumb then points in the direction of the magnetic field. Okay, so going again up and around, hands go up and around, thumb points in the direction. So that means this end would be our north end, and this would be the south. The same is true even if we use the opposite side. So remember, over here the current's coming out. So if we point our fingers in the direction of the current, oh, yep, direction of the current, here we go. And the magnetic field is still going to the left. So the north on this end and the south on this end. So how does that look on paper? And why does it behave like that? So here's our wire. Let's say we take a normal wire, just one loop, and we loop it around, send the current in on this side and out on this side. So there's our electric current. Now, if we use our right-hand rule again on this wire that's going up, let's choose, for example, this spot here. Okay, so if we point our thumb in the direction of the electric current and our fingers wrap around, we see that the field would be coming out on this side. So this is, the blue represents the magnetic field, and it would be going in on this side. Okay, if we take a look at another spot on the top, so now the current is going to the left, and again, the magnetic field on top is coming out of the page and going into the page in the center. And you'll see that the same thing happens here with the magnetic field going into the center and out on the outside of the loop. So what happens is, in the center, we get all the magnetic field compounded in the same direction from this loop. And that's why we have it travel through the solenoid, through the whole solenoid, rather than just looking at each individual piece of the wire. When we want to draw one of these solenoids on our page, I find it easiest to draw our core here. Okay, and then we can draw our wire. So our wire goes up in front and then down in the back, up in front, and I've run out of space, but then it would come down and back, and we can say that this is attached to a battery, for example. So let's just take a second then and figure out what it would be on this one. So remember, if we have a battery, let's figure out which end would be north and south here. So here's our battery. Okay, the current in this solenoid, we're using conventional current, so it comes from the positive side and goes into the negative. Okay, so here's our current. So our current's going in here. It's going up behind the solenoid and around to the front. So we would take our hand, follow it up behind the solenoid, and curl around to the front, and that makes the right-hand side, if we follow our thumb, the direction our thumb's pointing, this side would be north, and this side would be south. Okay, so that's the second right-hand rule. Again, just to reiterate, so that's when we have a solenoid, we wrap our fingers around the direction of the current, the way the coil is wrapping, and our thumb points in the direction of the north side of the magnetic field. Lastly, our third right-hand rule. So in the first right-hand rule, we saw that how when you have a wire, just a single individual wire, that wire creates a magnetic field of its own when you put a current through it. So what happens if you take that wire that's generating a magnetic field and you put that wire in a separate external magnetic field? Okay, then the two magnetic fields start to interact and we get a force that causes the wire to move. So for an example here, let's say we have I'll use blue again. Let's say we have a magnetic field going to the left. Okay, I'll make it a little bigger. Okay, here's my magnetic field traveling off to the left here. Okay, and let's say we put our wire in this magnetic field. I'm going to use the pencil for the wire again. Let's say we point the wire and we have the current going north through the wire. So the wire, we have an external magnetic field, the blue lines. We have our wire that has its own magnetic field when we put a current through it, current going in the direction of the point of the pencil. So then how does the force act in this situation? So for the third right-hand rule, again, we take our right hand. In this case, in the third right-hand rule, you take your thumb points in the direction of the current on the wire. Your fingers point in the direction of the external magnetic field. So for this one, my fingers are going to point to the left. My thumb is going to point directly up, okay, in the direction of the current. The force on the pencil is perpendicular to your palm. Okay, you'll see if you watch a lot of videos, you'll see a lot of different ways you can do the third right-hand rule. They're all essentially the same thing. This is personally the way I like to remember it. So again, fingers are the magnetic current. Thumb is the current fingers are the magnetic field. Thumb is the electrical current in the wire, and the perpendicular from your palm. So in this case, the force would be coming directly out towards you. So the pencil in this magnetic field, or the wire, would have a force on it moving this direction toward us. This third right-hand rule applies also to particles or electrons that are traveling through or other particles that can generate magnetic fields that are traveling in an external magnetic field. So a force on a particle, it's the exact same as the force on the wire in terms of how you use the right-hand rule. Okay, in the next video, we'll look at the equations and some math behind that. For now, let's look at another example. Let's actually just take this page. Let's flip it upside down. Let's send our magnetic field to the other direction. Let's take our wire. How about we put it on an angle like this? So our wire is traveling through. I can actually use the brown marker to represent our wire. Okay, our current is going in this direction. So using the right-hand rule, where would the force be this time? So again, we take our right hand. I have to move a little bit here we go. So our right hand, so fingers are pointing in the direction of the field. My thumb needs to be pointing in the direction of the current. So I'm going to have to actually flip my hand over, point my thumb on this diagonal here. There we go. And the force is going to be acting straight down out of my palm. So the force is going directly into the page, perpendicular to where my palm is facing. Okay, so the force in this case is straight down. Now you'll notice if the wire is here, or it could be going straight up, in both of those cases, even though one's on an angle and one's straight, the force is still directly down into the page. Okay, now the size of the force may differ a little bit, and that's what we're going to look at when we do our math behind all of this. So again, just to reiterate, we had our three right-hand rules. Should probably flip that around so you can see it. Our first right-hand rule was to find the magnetic field on a current carrying wire by pointing our thumb in the direction of the wire, fingers curl in the direction of the magnetic field. Second right-hand rule is to find the current on a solenoid. So our thumb in this case points in the direction of the north end of the magnetic field of the solenoid, and our fingers curl in the same direction that the current is going around the solenoid. And the third right-hand rule tells us about the force on a current carrying wire when that wire is inside its own external magnetic field. And again, this third right-hand rule also applies to the force on a particle in a magnetic field.